After a long period of little intellectual progress in Europe, renewal of commercial activity and urban development finally created a rising need for calculations. A new profession emerged called Maestri d'Abacus, or Masters of Calculation. You may have heard of an abacus before, and this indeed is where that word comes from. These men who dedicated their lives to math discovered many ways to speed up the calculating necessary for commercial activities, including calculations which dealt with large numbers. Today, we will dive into one method well known in the abacus tradition used to check for mistakes in calculations. Let's take a look. The powerful trick they used is called casting out nines. Let's work through an example. Behind me on the board, I have the addition problem 89 plus 21. Now this is equal to 106, but now we need to check our answer using this trick. So first we'll start with 85. What we do is simply just add the digits. 8 plus 5 is 13, but 13 is a double digit number, so we can just add its digits together. 1 plus 3, which gives us 4. Now 21 is a little bit easier. We just add 2 plus 1, and we get 3. So now we take both of those digit sums and add them to each other. 4 plus 3 equals 7. But if we look at our final answer down here, 1 plus 0 plus 6 also equals 7. So when we add the digit sums of our addends, we get the same number when we add the digit sum of our actual sum. This works no matter which numbers we choose to start with. This method might seem a little bit magical at first, but it really can all be explained with just math. This works because nines are one less than the number of digits we have in our decimal system, which is 10. When we add the digits of a number together, we really are just taking the original number modulo 9, which is a fancy way of saying we want to get the remainder after we divide the number by 9. This works because 9 is the same thing as adding 10 to a number and subtracting 1 from a number. So we add one digit to the tens place and subtract one digit from the ones place, or vice versa, and we end up with the same digit sum no matter how many times we repeat this process. Now that we've seen this trick works for addition, we can see that it works for all three of the other operators as well. Let's say we were subtracting these two numbers instead. Well, we can easily show that that subtraction is 64. Now, remember before, the sum of the digits of 85 ended up being 4. The sum of the digits of 21 ended up being 3. Well, now that we're subtracting, we should just subtract those two digit sums. So, 4 minus 3 gives us 1. Now, let's add the digits of 64, the answer to our subtraction problem. 6 plus 4 equals 10. 10 is two digits, so we add those two together. 1 plus 0 is 1. So, we still get our numbers match up when we do subtraction. Similarly for multiplication and division, if we just multiplied the digit sums together and then found the digit sum of that, it would be the same as the digit sum of the answer to the entire multiplication problem. And same thing for division. The digit sum of our quotient and remainder would match that if we just did the problem with just the digit sums. So, if this trick is so powerful, why isn't it so well known anymore? Well, the method was actually taught in elementary schools up until quite recently. While it is a very simple trick we can use, it isn't always the most practical in catching mistakes. For example, if I had done my math using 58 instead of 85 because I accidentally flipped two digits, well, the digit sum of 58 and 85 doesn't change. Addition's commutative. So this method wouldn't actually help me catch my mistake in that case. Additionally, this trick was used to catch mistakes on calculations using very large numbers. Well, I just used two-digit addition and subtraction. The problem is, elementary schoolers don't really need to do calculations on very large numbers to show that they've mastered the skill. Once they can add 2 and 3-digit numbers, then we know that they can extend that skill up to higher digits. This method does actually have applications in computer algorithms and computing methods, but is no longer practical for elementary use. Well, that's it for now. In our next math history video, we will be sticking around in Europe. Please like and subscribe so that you don't miss it. See you next time.